This is the Level 3 Physics Electricity video on capacitors. So first up, what's a capacitor? There's some pictures of capacitors, and they all look, a lot of them are quite circular or cylindrical, but it turns out that that's what you see on the outside. What's on the inside of a capacitor is you've basically just got two metal plates. And this is how we draw it. So these things off to the side here are wires, and these are my plates of metal. So just, I guess, sheets of metal is another way to describe it. And on one side, we have a bunch of positive charges, and on the other side, we have a bunch of negative charges. And that forms an electric field in the gap between. So here's my gap. And I can put my electric field lines like this. So I can form an electric field between these two plates. So why do these look cylindrical? Well, to save to save space, we get these big plates. We put something in between them, and we'll talk about that in a second. It's called a dielectric, and we just roll them up. So these here are just rolled up plates of metal. Two plates. The plates themselves, they form this electric field, and one of the purposes of a capacitor is to store energy in that electric field. The thing I just briefly mentioned was the thing that goes in between the plate. So here's my two plates, and we can put a substance in between here. That was a very badly drawn box. This substance is called a dielectric. And for one, it's an insulator. So it doesn't It doesn't conduct electricity. So the positive charges and the negative charges. The negative charges can't get through the positive charges, but it can become polar. And what that means is the atoms in here, there's a whole bunch of atoms in here, they can end up lining up in the same direction. When they line up, the atoms line up. When those atoms line up, what we get is an increased magnetic field. Increased electric field. What am I talking about? So by putting this material in here, and examples of this can be plastic. There's different types of materials that have different strengths because they have different abilities to become polar. In between the two plates, our dielectric goes in between the two plates. The atoms in the dielectric line up, and this increases the electric field, so it makes the capacitor better. And once again, this is called a dielectric. How does a capacitor work in a circuit? This is my symbol for a capacitor here. I've got my battery at the top here, the positive side and negative side. I've got my light bulb. I'll just label this capacitor, bulb. I turn the circuit on. Let's say there was a switch here, and I turn it on. Current flows this direction, but we know electrons flow in this direction. So my electrons come around this direction. They go through the bulb. The bulb lights up for a little bit, and the electrons end up accumulating on this plate here. They can't jump across to the other side because there's a gap there or an insulator in there. And so what they do is the electrons on the other side are forced away from this. A lot of electrons are pulling up here, and they force all the electrons here away and of course towards the positive end of the battery. In forcing the electrons away, you end up being left with a positive charge on this side. So this is how our capacitor works. After a while, we'll talk about this in the next video, no more electrons will flow because we've got the maximum amount we can on this plate. So there's a couple of formulas you need to know. The first one is C is for capacitance. It's measured in capacitance is measured in farads, which is symbol F. And just so you're aware, a lot of the capacitors that we use in everyday life are the amount of capacitance in farads is very, very small. So you'll get numbers like 22 microfarads. B is the voltage in that circuit. and Q is for the charge. It's stored on either side of the capacitor. The second formula is how good a capacitor is given by, so again, capacitance, same as in the formula above in farad, is given by this one. So this is how we build a capacitor. So the D is the distance between the plates. Distance between plates. Here's my plates, and that's in meters. A, let's just go here, is the area of the plates, and that's in meters squared. This one here is a number, and it is the strength of the dielectric. We call it the dielectric constant. So if you have plastic in there or glass in between or some other material, they'll have a different number. And it's a number. So it could be 2, it could be 8.5, which means this dielectric is 8.5 better than if there was nothing in between. It could be whatever. And the last one is another constant, and this is a constant that doesn't change. This is called the permittivity of free space. I'm going to write that word out. Permittivity of free space. And that is a number that's given to you on your formula sheet, 8.85 by 10 to the minus 12. That's a 12 farads per meter. The last formula, it's not going to fit there because I've written dielectric constant. I'll write it anyway. This is the energy stored in an electric field, a half times QB. Cool. So those are the three main formulas for describing capacitors in simple DC circuits. The last thing we'll look at is what happens if you put a couple of capacitors in a circuit. So we can put them in series or we can put them in parallel. I think we'll start with parallel first. Makes more sense to me. In a parallel circuit, we've got electrons coming out of the negative end. Some of them will end up here. Some of them will end up here. And we get positives on this side, lots of positives. And so what have you got in this case? Well, you've got two capacitors storing a bunch of charge. You've got twice as much ability to store charge. So in parallel, the total capacitance is just add up what's in the circuit. In series, however, your negatives go around, negative, 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 pushes the negatives away from here, negative, 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 pushes the negatives away from here. If you were to unplug these and plug them into something else, what ends up happening is these negatives and these positives end up cancelling each other out. And so it's really like you've only got this side here and this plate here left over, negative, 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 positive, 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 but with a bigger gap in the middle, a bigger distance. And from the formulas you were looking at before, you had this one here, where when you increase the distance, you actually decrease the capacitance because it's an inverse relationship. And so the formula for putting two capacitors together in series is this one here, 1 over C1 plus 1 over C2 plus dot, 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 dot. Now they should look familiar because they look very similar to how the resistance formulas are set out, except they're the opposite way around. A resistor in series looks something like, add them up. Whereas a resistor in parallel is your 1 over. So if you just think of your resistor ones but swapped around, it makes sense for what a capacitor is.